Hi friends, in our last session we have seen syllabus of our subject machine tool design and also started with our chapter number 1, that is introduction to machine tool drives. In today's session we are going to see the general requirements of machine tool design and what is working motion and auxiliary motions. This is Fazan Kagdi and I welcome you all to our lecture series of machine tool design. So let's begin with our first topic, that is general requirements of machine tool design. So as you can see, the list is provided. The first major requirement of machine tool design is high productivity. Second requirement is ability to provide required accuracy of shape and size along with the necessary surface finish. Third, simplicity in design. Fourth, safety and convenience of controls. Fifth one is good appearance, and sixth is low cost of manufacturing and operation. So we are going to discuss all these points in detail. So let us start with our first point, that is high productivity, which is a major requirement of a machine tool design. So now as you can see on your screen, P is equal to 1 upon TC plus TNO into eta. Now what is TC and what is TNO? So you would say TC is a machining time. That is a time required to produce a finished component or a finished work piece. We can say in how much time a finished component can be produced. So that time will be TC. Okay, next time is TNO. So TNO, as you can see, it is a non-productive time which does not contribute to our machining process. That time does not contribute to our machining process, remember. So what it includes? So we can say it includes ideal travel of a cutting tool before commencement of a cut, then after ideal travel of a cutting tool after completion of a cut to its initial position. Then we can say clamping and unclamping of a workpiece, right? Then we can say loading of a cutting tool, right, to a tool post, that is on a carriage. So all this time contributes to a non-productive time. Also there is a factor called eta. Now this factor eta takes into consideration of a sudden stoppage of a machine tool. Now when a stoppage can take place, so because of sudden accidents, right, or we can say for doing a maintenance of a machine tool, so that factor eta will always be less than 1. So as you can clearly see that if TC is higher, machining time taken is higher, and TNO is also higher, then productivity of our machine tool will be reduced, that is it will going to decrease. Okay, so our first target is to increase the productivity of a machine tool. Okay, that factor is most important. Now let us see that how we can achieve that. So we can increase the productivity by first cutting down a machining time. For cutting down a machining time, we need to provide high cutting speed and feed rates. Along with that, we can say that at a time of design itself, we should provide a machine tool with a future accommodation. That is, there must be certain facilities provided that it could adopt a future development. A machine tool could adopt a future development. Otherwise, it will become obsolete. Right. Next, we can say that simultaneous multiple cuts and coolant can also reduce the machining time. So this will all contribute to reduction in a machining time. Next, how we can cut down the non-productive time in order to increase the productivity. So by making use of jigs and fixtures in order to reduce the clamping and unclamping time, that is loading and unloading of a workpiece can be directly reduced. We know we have different types of arrangements such as angle plates, right? Even we have a taper turning attachment, which is one type of a fixture for doing a taper turning, right? Even we have a compound slide, but when a working size is larger, then for that we need to use a taper turning attachment. Okay, this is again one type of a fixture. Okay, and next we can even reduce the non-productive time by making use of more than one tool simultaneously. So you have an example for that, that is external turret lid, hexagonal turret, right? On that we can mount 6 cutting tools simultaneously. Okay, now let us see further. Improving reliability to reduce breakdown and unscheduled stoppage. So this point is related to our factor eta. So higher is the reliability, we can say higher would be eta and it will increase the productivity. Next point is to improve the accuracy is a major requirement for a machine tool design. Now over here, accuracy means we need to improve geometrical accuracy and kinematic accuracy. Now let us discuss about geometrical accuracy. So improving geometrical accuracy, which means that there would be guideways and or we would say slideways provided on our machine tool bed. Okay, for example, lathe machine, so there is a guideway provided on which we can say a tail stroke is going to move, right? It is going to perform a linear motion. Similarly, a carriage is going to move and it's going to perform a motion that is for a feed motion of a cutting tool, right? So on what it is going to move? So we can say it is going to move on a guideways. So it is very much necessary that guideways dimensions are accurate. There should be no misalignment of a guideway. Otherwise, what could happen? Other than it could lead to inaccuracies of our workpiece, right? So this is most important. We need to improve geometrical accuracy. Otherwise, it could even lead to a jerk and vibrations. Next, we need to improve kinematic accuracy. Now, this kinematic accuracy is related to our machine tool gearbox, which means that the gearbox should be such that it occupies minimum space. Remember, compactness. Second, the gearbox should provide a maximum speed ranges. Remember, maximum speed ranges. And even on an output shaft of a gearbox, there must be minimum number of gears, and it is always optimum to take 2 gears on an output shaft, so that that output shaft will be directly connected to our machine tool spindle. Remember, so for that, kinematic accuracy is going to play a most important role. All these factors are going to come under kinematic accuracy. That that topic, entire topic will be discussed in our chapter 2, that is design of multi-tool machine tool gearbox. Okay. Next point, we need to increase the static and dynamic stiffness of a machine tool. Now first of all, let us understand that what is a static stiffness. So stiffness means resistance to deformation. Resistance to deformation. Now static stiffness means resistance to deformation due to static load. Remember, due to static load. Now because of this static load, bending of a structure can take place. Taking a simple example of guideways. On a guideway, we know tailstock is going to move, right? And carriage is also going to move. Now because of a weight of a carriage and tailstock, we can say a deformation of a guideways can take place. Why? Because tailstock and carriage is going to exert a load, that is a static load. So the structure should be such that it should resist the deformation due to this load. So it is required to increase the static stiffness. I hope that you are getting. Okay. Next, we need to provide a dynamic stiffness. Dynamic stiffness means a motion, a stiffness or resistance to deformation at a time of motion. Which means when a cutting operation are performed, there are mainly two forces because of which vibrations takes place. That is inertia force and pulsating force. Because of inertia force and pulsating force, deformation of a structure as well as machine, a structure as well as we can say workpiece can take place. So that has to be avoided. For that, we need to increase the dynamic stiffness. Okay. And this topic of static and dynamic stiffness we will discuss in detail in our chapter 3, that is machine tool structure. Okay. Now let us see further. That is the next requirement is simplicity in design, which we have seen. So design can be simplified by using a standard parts and sub-assemblies. It provides ease of manufacturing and operation. That is, if we use the standard parts and sub-assemblies, then manufacturing and operation performing will be quite easier. Okay. Taking an example that a general purpose machine tool is more complex than a special purpose machine tool, as it puts restriction on a range of several operations. Next point is safety and convenience of control, which means we need to provide safety to a worker as well as our machine tool, and convenience of controlling the machine tool to our worker. So in this first point, as you can see, we need to provide shielding to our rotating part as well as the moving part. That can be done by means of hoods. So which are our rotating parts? So we can say that spindle is going to rotate, right? We even have a lead screw which is going to rotate. That is a primary cutting motion will be performed. right? Similarly, we can say that moving motion, that is a carriage is going to perform a linear motion, telescope is going to perform. So we need to shield all these parts so that accident could not occur. Okay. Next point, as you can see, we need to protect the worker from chips, abrasive dust and coolant by means of a screen or shields. Which means you know that helmet, most of the times worker wear the helmet. That is a type of a shield, glass is taken by the worker to protect themselves against coolant and chips which are coming from a workpiece. Okay, precluding the possibility of accidental pressing of push buttons and handles, which means we can say that by ignorance of a worker or by accident we can say that push button of a machine tool is pressed or a hand wheel is rotated at a time of operation. So this could create accident, right? This could be avoided. This has to be taken into consideration while designing our machine tool. Okay. Next point, as you can see, providing reliable earthing of a machine to resist against a sudden shocks. Okay. Next, last point, as you can see, provide device for safe handling of heavy workpiece. Which means you know that we need to lift the heavy devices by means of overhead cranes, right? So the hook is going to lift the portion and carry it up to a certain location, right? So material handling plays a most important role in case of a heavy workpiece. Okay, now let us see our next point. Now, appearance. So it is very obvious that if a good appearance is provided, it is going to improve the working condition and a mood of an operator or a worker. This can be done by painting and color codes. Most of the times you would have seen a gray-green color or a green-blue color applied on our machine tools, right? So what does this create? So this creates a bright and a pleasant atmosphere. This is going to attract the worker to do more and more work. Okay. Next point, sixth one, as you can see, low cost of manufacturing and operation. Now, this basically depends on how we can reduce the cost. So this depends on a complexity of a design and material of construction. For instance, we can say that considerable saving of metal or a reduction in volume of a metal can be achieved by making use of a welded steel structure instead of a heavy cast iron parts for manufacturing of beds, for manufacturing of columns and base of a machine tools. Okay, so compared to cast iron, we know that steels are lighter in weight. Okay, now this will make transportation and installation of a machine tool easier and quite cheaper, and ultimately we can say it is going to reduce the cost of manufacturing and operation. Okay, so these are all the general requirements of a machine tool design. Remember, 6 points are there. Okay, that is high productivity, then accuracy has to be achieved, that is geometrical accuracy, okay, kinematic accuracy, and static stiffness and dynamic stiffness has to be increased, right? Then simplicity of design has to be achieved, then safety and convenience of control has to be provided, proper appearance to a machine tool has to be provided, low cost of manufacturing and operation. These are all the requirements we need to keep in mind. The most important question. Okay, so now let's proceed further. Next we need to see working and auxiliary motion of a machine tool. The first question comes that what is working motions? So we would say that the motions which are required to impart a required shape to the workpiece, that motions are called working motions. Remember. Okay, so we know that there are two main parts, that is one is a workpiece and second one is a cutting tool. In case of a lathe machine, as we all know that a workpiece is attached with a spindle of a machine tool. It is going to rotate at a high speed, workpiece is going to rotate, and a cutting tool is going to perform, let's say, a horizontal motion. That is a turning operation we need to perform, right? So these two motions, one is a horizontal motion of a cutting tool, the second is a rotary motion of our workpiece. So these two motions we can say are called working motions. Okay. So in general terms we can say that working motions are classified into two categories. So the first one, as you can see on your screen, drive motion or primary cutting motion. Even it's called a generatrix, which means this drive motion is our mechanical power, rotary motion of a spindle. Remember. Okay, and second one is a feed motion, that is even called a directrix. Okay, so this is a motion of our cutting tool in case of our lathe machines. Okay, so working motions we can say further are of two types. That is, it could be a rotary motion or it could be a translatory motion. Translatory motion, which means a linear motion. Okay, so taking a simple examples, let us see further that for a lathe machine and for a boring machine, what will be the drive motion? So the drive motion will be a rotary motion of our workpiece. We are going to see the figure, you will get a more clear view. Okay, and what is a feed motion for a lathe and a boring machine? So we would say translatory motion of a cutting tool in an axial or radial directions. So let us see further. Now, as you can see on your screen, the diagrams are shown. So first diagram is for a lathe machine. As you can see, a rotary motion is provided to our workpiece. That is, let's say workpiece is rotating in an anti-clockwise direction, whereas there is a cutting tool provided. So a horizontal arrow, as you can see, is shown. So this represents the motion of a cutting tool, and this rotary motion represents the motion of a workpiece. So this motion is called a feed motion, and this rotary motion is called a drive motion. Okay. Now, taking an example for a drilling machine. So what will be the drive motion for a drilling machine? So over here, the drive motion will be a rotary motion of our drill bit. Okay, that is of a cutting tool, drill bit. It's going to be fed in a downward direction, whereas workpiece is going to remain stationary. Remember, which means both drive motion and feed motion is provided to our drill bit. Okay, rotary motion as well as a downward feed motion. You can see on your screen, it is shown for a drilling machine. Drill bit is rotating and a downward motion of a drill bit is there, which means a downward motion means feed motion is provided. Okay, so this is for a drilling machine. Similarly, we can say that for a milling machine. Now, what is the purpose of milling machine? We should know that. The purpose of milling machine is your manufacturing, right? So the drive motion in case of a milling machine is a rotary motion of our milling cutter. Okay, you can see on your screen a milling cutter is shown. Okay, it is going to rotate. So we can say the mechanical power is given to our milling cutter, and workpiece is going to perform a translatory motion. Okay, that is a linear motion of our workpiece. Okay, now let us see further. Next example, we can say for a shaping, for a planing, shaping and slotting machines. So what will be the drive motion for a shaping planing machine? So we can say a reciprocating motion of our cutting tool. Okay, that is our drive motion. So in this case, remember, reciprocating motion, that is a linear motion of a cutting tool is a drive motion. Okay, now what is a feed motion? So feed motion is an intermittent linear motion of a workpiece. Over here you can see in this diagram, right? You can see the shaping machine example on the top right corner of your screen. That is a linear motion of a, we can say a linear motion of a cutting tool is shown, and a translatory motion, intermittent translatory motion of a workpiece is shown. Okay. Now next example is for a grinding machine. So over here please see clearly that for a grinding machine, the grinding wheel is going to rotate, which means a drive motion will be given to our grinding wheel. Okay, whereas the workpiece will rotate as well as it is going to perform a translatory motion, that is a linear motion. Okay, so we are going to see the example for that. For grinding machine, drive motion will be a rotary motion of a grinding wheel, and feed motion will be a rotary as well as we can say translatory motion of our workpiece. So these motions, remember, drive motion and feed motions are called working motions. These motions are going to impart required shape to our workpiece. Okay. Now the next type of a motion is called a auxiliary motion. So we would say that this motion does not participate in imparting a required shape to a workpiece. This is not going to participate in a machining operation, remember, but it is going to help the working motions to perform their task. Remember, it is going to help the working motions. It is necessary for a working motions to perform their task. Okay, so what are the auxiliary motions? Let us see the examples. So as you can see on your screen, that is clamping and unclamping of a workpiece. That is loading and unloading of a workpiece on a machine tool spindle. It is a motion which is done by an operator, right? So it is an auxiliary motion. Next, ideal travel of a cutting tool to the position from where a cutting has to be begun, right? So ideal travel before commencement of a cut, and ideal travel after commencement of a cut. So this comes under the category of auxiliary motion. Next we can say changing the speed of a drive and feed motion. So a worker is going to do certain lever, it's going to rotate a certain lever, which means we can say that worker is going to perform a motion. So what is that? We would say auxiliary motion for changing the speed. Similarly, engaging and disengaging of a working motion. So this all comes under the category of an auxiliary motion. Okay, so let's see the next slide. Now on your screen, as you can see, in case of a machine tool, we can say working motions are powered by electric motor. Okay, how working motion is performed? So power source is an electric motor, whereas the auxiliary motions are carried out manually, or it may be a power operated depending upon a degree of automation. Whereas in case of automatic machines, we can say CNC machines, computerized numeric control machines, the auxiliary motions are automated and are performed by machine itself. Okay, which means the automation is given to auxiliary motion also. Okay, so in today's session we are keeping up till here. So what we have discussed in our today's session, let's take a quick overview. That is general requirements of a machine tool design, and second, working motions and auxiliary motions for different types of machines. Okay, in our next session we are going to discuss the parameters required or we need to consider for working motions. Okay, along with that we are even going to start with machine tool drives, that is different types of drives, hydraulic drives, mechanical drives and electric drives. So till then, stay tuned and thank you all.